All right, now in part two, I want to learn how to deal with the individual components of that transfer function. So let's do an example here. Let's say I have h of s equal to 1 over tau s plus 1. In this particular case, I'm going to analyze this guy with tau equal to 0.001 seconds. Okay? All right. So this guy's got a single pole. Okay? That pole exists at s equal to minus 1 over tau, or negative 1 over 0.001 seconds. All right, so that equals minus 1,000. And even though that's in seconds, it's actually in rads per second. Okay, so minus 1,000 radians per second is where that occurs. All right, now let's plug in s equal to j omega. Okay, so I have h of j omega equals 1 over j omega tau plus 1. Okay, so we'll take the magnitude of that guy. So 20 log 10 of h of j omega, magnitude. All right, so again, I can just do this like I did before. So this is 20 log 10 of 1 minus 20 log 10 of the denominator, which would be 1 plus omega squared tau squared square rooted. Okay, if you don't remember how to do this, go back through the first part of the lecture and it's all there. All right, now a couple of things to remember. So I got a constant of 1 here. A log of 1 is 0, so that term is gone right off the bat. Now when it comes to this term, okay, so let's write this guy here, minus 20 log 10 1 plus omega squared tau squared. All right, when I look at this, I say there are two regions for this guy. I'm going to make an approximation. Okay, let's first say that I'm looking at omega much, much less than 1 over tau. So in other words, frequency is much, much lower than the location of this pole. Okay, for frequencies much, much less than the location of this pole. All right, or another way of thinking of this is omega tau much, much less than 1. Okay, this is what I call low frequencies. Okay, so in this low frequency range, I have omega tau much, much less than 1. Now at this particular point, okay, I'm going to make some approximations to this guy. So I'm going to say this guy is approximately equal to, if omega tau is much, much less than 1, I can say that this term, this omega squared tau squared term, is much, much less than this guy. So I can approximate everything under the radical. It's just 1, right? In other words, I can say this guy's really small in comparison to 1, so I'm going to ignore him. So I can say this is approximately equal to minus 20 log base 10 of square root of 1, which, if you evaluate that, is equal to 0. Okay? So for really, really low frequencies, what I'm saying is that 20 log of the magnitude is equal to 0. Okay? So it's a constant, and it's a constant that's equal to 0. Okay? Now, the other approximation that I'm going to make, actually, let me just go straight down here. The other approximation I'm going to try to make is I'm going to say, well, what happens if omega is much, much greater than 1 over tau? What would be high frequencies? Okay? At that point, omega tau is much, much greater than 1. All right? So if I look at this term here under the radical, right? If omega tau is much, much greater than 1, that means this term under the radical dominates, and the 1 becomes negligible. That means I can approximate this guy now as minus 20 log base 10 of omega squared tau squared, like that. Okay? It's kind of an interesting result for me. Okay? Now, what does that tell me? Okay? Well, couple of things, right? So if I look at this, it tells me I can sort of break this down. I have a square root of some stuff squared, so that says that this is equal to minus 20 log 10 of omega tau, or I can write that as minus 20 log 10 of, again, if I have the log of a product, I can say that's the sum of the logs. So minus 20 log of omega minus 20 log 10 of tau. Okay? In other words, what I've said is that 20 log 10 of h of j omega is equal to minus 20 log 10 of omega minus this guy. Now, if I step back from this, I know that tau is a constant, right? And I can sort of look at this and say, well, let's think about this as y, okay? I can think of log 10 of omega as x, just a variable. Replace log of omega with x. That's the case. What I have is a linear relationship. Minus 20, y equals minus 20x plus b, okay? This is a linear function, okay? Now, that it's a funky linear function because I have my x is actually equal to log of omega. All right, so what I do to look at this is I say, well, let's try to plot this guy. Let's say I have a y-axis, which is 20 log 10 of h of j omega, okay? And I have an x-axis, which is log base 10 of omega, okay? Like so. And I look at this and I say, okay, so this is a linear scale, so this is my origin, okay? So this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, right? So I've just drawn, stuff spaced linearly, just integers spaced linearly. Each of these corresponds to the log of a particular number. Okay, so 0, 1, 2, 3, 4, 5, 6. Each of those corresponds to the log of a particular number. Now, if I go to here, okay, I've written out here, I'll just keep it like this. What I keep in here is I've said, okay, so this was my x. Log 10 of omega was my x. What I see here is that for x equal to 0, right? If omega was equal to 1, the log of 1 is 0. If omega was equal to 10, the log of that would be 1. If omega was 100, the log of that would be 2. 1,000, it would be 3. 10,000, or 10 to the 4th, and it would be 4. What I see is that on that x-axis, where x equals the log of omega, each integer value here, 1 represents 10, 2, 100, 3, 1,000, 4, 10,000. As I go up by 1 on the log scale, I go up by a factor of 10, or what we call 1 decade, okay? So for every number 1 that I go up on the log scale, I essentially go up by a factor of 10 in frequency. So if I go back to this picture here, all right, if I go back to this picture here, what I see is that 0, my origin, corresponds to a frequency of 1. All right, so sometimes I dimension my axis like this. So 0 on the log scale is 1 in frequency, 1 is 10, 2 is 100, 3 is 10 to the 3rd, 4 is 10 to the 4th, 5 is 10 to the 5th, 6 is 10 to the 6th, okay? All right, now, I've dimensioned that guy, and apparently what I want to do now is I want to say, all right, I want to use these approximations, okay? So back in my original example, I said let's look at this system. Let's let my tau be equal to 0.001. So 1 over tau is 1,000 radians per second. Okay. All right. So I was looking at frequencies much less than 1 over tau, and frequencies much greater than 1 over tau. All right. In this case, 1 over tau is right here at 10 to the third. For sake of argument, let's say that frequency is much less than 1 over tau. All right. Let's say that that goes up to a factor of 10 before the 1 over tau. All right. So in other words, in this case, if 1 over tau is at 1,000, let's say much less than 1 over tau goes up to 100. Right. Now for those low frequencies, we said that this guy here, our y value, 20 log 10 of omega, was equal to 0. Okay. So I'm going to sketch that in. So this guy is equal to 0. Right? Now, what happens for high frequencies? Well, high frequencies, I said that our y value, 20 log of the magnitude, is related to negative 20 times our x value plus a constant. Okay, so that means for every factor of 10 in frequency, so for every number here on the x-axis, I'm dropping 20 on the y-axis. All right, so for every decade in frequency, I'm dropping 20 decibels. Okay, so I write here negative 20, negative 40, negative 60. Each one of these guys represents a factor of 10 in magnitude. Okay, so if I begin this, all right, so again, our omega is in this case, our tau is such that 1 over tau is at 1,000. I said omega must be much greater than 1 over tau to have this sort of behavior. All right. So I'm going to say, let's assume that much higher than 1 over, or much higher than 1,000, let's assume is 10,000. All right. What's happening at those frequencies, okay, those high frequencies, is that I have a linear drop for every number that I go up here, meaning every factor of 10 in frequency, I drop 20 on my y-axis. So I show that as just a linear relationship here. Okay. And it looks something like this. Okay. I write this guy as negative 20 dB per decade. All right. Now, if and again, I can put in there this, minus 20 log 10 of tau. All right. Now, let's just make the assumption, right? We don't know what should happen when omega is approximately 1 over tau. Right? It's not clear. Let's just assume that this guy extends all the way to here, all the way to 1 over tau, and that this guy extends all the way to 1 over tau. Okay? So in other words, let's just assume my magnitude is such that my low frequency approximation holds right up to 1 over tau, and my high frequency approximation begins right at 1 over tau. Okay? Let's just make that assumption. Now we go to MATLAB to try to see how good our assumption is, and here's the picture we get. Okay, so notice what we see here, right? In this case, so 1 over tau is 1,000, right? My black line here is my approximation, and the blue is the actual plot that MATLAB generates. What I see is that right up until about here, right, which is less than a decade from where my actual pole is, it's a pretty good approximation, right? And then less than a decade away, it looks like the blue and the black are pretty much following each other yet again. It's only right in this little small area right here where there's a discrepancy between the two. And we can actually explain that discrepancy relatively clearly, right? So let's do that real quick. If I took 20 log 10 of the magnitude of h of j omega, and let's say I evaluate this explicitly at omega equal 1 over tau, right at the pole frequency. Well, that would be 20 log 10 of 1 over 1 plus omega squared tau squared. Again, if I evaluate this at omega equal 1 over tau, this would simply become 20 log 10 of 1 over the square root of 1 plus 1, or 20 log 10 of 1 over square root of 2. Now if I calculate 1 over square root of 2, right, that's approximately equal to 0.707, okay? This guy becomes minus 3 dB, okay? If you evaluate this, the number you get is minus 3, okay? That's where we get the term the minus 3 dB frequency. In other words, right at the pole frequency, omega equal 1 over tau, the value of the transfer function is equal to minus 3 dB. More importantly, right, what this says is that at a frequency, that at the pole frequency, my transfer function has dropped to 70% of whatever my low frequency value is, okay? 70.7% of that value. It's dropped 3 dB below that. Okay, what you can see really is sort of the important thing here, right? The important thing is that if I have a single pole, I can approximate the magnitude as being constant at 0 dB right up until that pole. And then once I reach that pole, I can approximate it as falling off at a rate of 20 dB every decade. Okay. Now, what's important about that, if I go back to my magnitude relationship here, right? If you look at a pole, it has the same shape as a 0, right? In other words, if you go back through the math that I just did, you would get the exact same results for a pole as you would for a 0, okay? And so what that means is that for a pole, right, I'm constant at low frequencies and then dropping at 20 dB per decade at high frequencies. So for a pole, my magnitude is constant and then dropping. For a 0, it would be constant at low frequencies, and instead it would be rising because I have a positive sign on here. All right, so zeros cause us to rise at 20 dB per decade. Poles cause us to fall at 20 dB per decade. Okay, so in both cases at low frequencies I have a constant and then I begin to change. So for a pole, I'm constant and then I fall 20 dB per decade. For a 0, I'm constant and then I rise at 20 dB per decade. That behavior is important, and we'll need to know that when we design control systems. All right, now, back to my single pole example. All right. So here in my single pole example, I want to look at him a little bit more carefully. Okay. All right, so I also said that I need to look at the angle. So if I want to look at angle of h of j omega, okay, that's the angle of 1 over j omega tau plus 1. That's the angle of 1 minus the angle of j omega tau plus 1. Okay, so the angle of 1 is clearly 0 degrees. The angle of this guy is minus arctan of omega tau. Okay, like that. Okay, so what's that look like? Well, I go to MATLAB and I plot that. If I look at what that looks like on a logarithmic scale, here it is. Okay, what I observe is that initially the angle is close to 0 degrees. Okay, eventually the angle drops to negative 90 degrees. Now, what I've shown on here is an approximation that we sometimes make. Right? It's not as common to do anymore because MATLAB is obviously very good at doing this. Right? What is shown here is the arctangent function, the blue. That's what MATLAB plotted when I ran the Bode command. And then I have this sort of straight line approximation. What I can see is that my straight line approximation and my actual are exactly equal to each other right at the pole frequency. And in fact, what they're equal to is minus 45 degrees. So let's check that. If I take the angle of h of j omega, when omega equals exactly at the pole frequency, I would get minus arctan of omega tau. So if omega is equal to 1 over tau, that's minus arctan of 1, or in this case, so what angle has a tangent of 1? 45 degrees, right? So I get minus 45 degrees, right? So right at the pole frequency, my magnitude is equal to minus 3 dB in the log scale, or 0.707 in the actual magnitude scale. And this guy is equal to minus 45 degrees, okay? All right, so those are two important results for me. Now, what have I shown here, right? What I see that's important is for low frequencies. So at low frequency, okay, I see that the angle of h of j omega is approximately 0. At high frequency, the angle of h of j omega is approximately minus 90 degrees. So a pole always causes my phase to drop eventually to minus 90 degrees. Now what I see that's kind of important is that, and it's somewhat important, it says that the transition from 0 to minus 90 happens over approximately 2 decades, okay? And it starts to drop approximately 1 decade before the pole and is done dropping about 1 decade after the pole, right? So start dropping about 1 decade before and done about 1 decade after, okay? Now then, that's sort of an approximation, right? But it's sort of a reasonable approximation. Sometimes we say that, okay, well, between those two, you can draw a straight line. Now that is, of course, an old school approximation. MATLAB is obviously much better at doing that than we are. Now, I will make you do that a little bit by hand again, just develop some intuition here in the next homework, right? But again, it's just to develop a little bit of intuition. You can easily check yourself with MATLAB, and I expect you to do so. All right, so this is what a pole does. What happens if I have a 0? Okay, so here's the overall angle of the whole thing. Well, so here for a pole, right, I have an arctan with a minus sign in front of it. For a 0, I have an arctan with a plus sign in front of it. So for the pole, I go from 0 degrees to minus 90 degrees, right? For a pole, I go from 0 to minus 90. For a 0, what am I going to do? Well, it's the same thing, except there's a minus sign in front of it. So I'm going to go from 0 degrees up to 90 degrees, okay? So for a pole, I go from 0 to 90 eventually. For a 0, I go from 0 degrees to 90 degrees. For a pole, I go from 0 to minus 90. So poles drop the phase, zeros increase the phase, all right? That's also an important result that we're going to need, okay, later on, all right? So what we see is that this is important. Now that I know these effects, I can look at a really complicated transfer function, and I can look at the phase of each pole and 0 separately, and I can add them to get the combined effect. All right. Same thing can be done. Same thing can be done for the magnitude. Right. Same thing can be done for the magnitude. I can get the effect of individual poles and individual zeros and add them up. All right. Now we need to look at more examples of this, which we'll do here in the next portion of the lecture.